capacitors also store energy. When we draw the capacitor with its voltage and its field and its charge, we think of it as storing charge, and it does store charge. But a lot of times sort of the point of a capacitor is to store energy in a circuit. Now let's be clear, but not enough to replace batteries. In terms of long-term storage, capacitors are a problem. They kind of leak. You may have noticed our little voltage went down in time a little bit during our demo. Well, they do make fancier capacitors than that, but they do leak, and it's just hard to get enough charge in there. You can read about supercapacitors. That's an effort to get as much energy as we can in capacitors, because they deliver the energy very fast, much faster than a battery can, but they can't hold nearly as much. So let's think about this. How do they store energy? How much energy do they store? So I'm going to draw a capacitor here, and I'm going to draw it getting a little bit into what it really looks like. Here's the metal wire that comes to the capacitor, and here's the other plate here. Other metal plate like that, starting to look like a real circuit element. And if we charge it up, we put some positive charges on that plane and some negative charges on that plane. So it has some capacitance C and it has some delta V. Okay? So the question is, how much energy? Which I'll call U. How much potential energy is in there? So you might look at it and you think back to our learning sequence on potential, and you'd say, well, if you have a charge Q at some potential, then that's the energy. You just multiply the potential times the energy. So you might say U is just Q times delta V, right? And then say, well, Q from what capacitance is C times delta V. So that is that times delta V. Just bringing that down. So you might say it's C delta V squared, right? And you would be wrong. It's not C delta V squared. No, it's not C delta V squared. I worry about writing incorrect equations. That's why I instantly scratched it out. It's not that. And here's the reason. It is true. You have a charge Q at some potential V, but when you put the charges there, and you did the work to put the charges there, it wasn't at delta V. When you put the very first charge on there, the delta V was 0. It was just two neutral plates. Okay? So when you add charge, you build up the delta V. It wasn't there the whole time. So what you have to do to see it build up, let's watch the charge build up and think about it. So what we have to do is think about differentials. What little bit of charge du do we get when we add a little dq? Well, it depends on what delta V was at that time. Okay? So delta V here is a function. It's a function of how much charge is on the plate. So each charge you add will add some energy. How much? Whatever delta V is. If it's 0, it won't add any charge. So let's now put in the function and integrate. Okay? So we're going to integrate both sides. That's just going to give us U, the total energy. The function, delta V, is Q over C. It's how much Q you have, how much charge is on it over its capacitance. And I went to Q because I have a dq here. Okay. And we're building up the charge all the way from 0 to big Q, the amount of charge on the capacitor. There you go. So do this integral, and it's equal to 1/2 1 over 2 C Q squared over 2C, if you do that integral. Evaluated from 0 to big Q, like that. Of course, the 0 gives you 0. So you get that the energy is Q squared over 2C. And if you want to, you can write the Q as C delta V. C delta V squared over 2C, and then you get, let's see, that C cancels one of those. You get 1/2 C delta V squared, if you want to do it in the same terms as you did over here. So it's not C V delta V squared, it's 1/2 C delta V squared. And the factor of 1/2 is because the charge had to build up over time. So we looked at our capacitor, and it was pretty small, 18 picofarads, and it was pretty big, 16 centimeters across. So you can imagine we would like larger capacitances in smaller things. So we're going to figure out one way to do that is to put an insulator in a capacitor. We haven't talked about insulators that much. We mostly talk about metals. So insulators are just these things that we could charge up by rubbing and use them to move charge around. They actually do a little bit more than that. So let me draw real quick our capacitor. So our two plates, negative plate over here. Standard capacitor. And we know it would create a field if we did nothing. We know it would create a field E naught. And we know that E naught is equal to sigma over epsilon naught. If each one of these had a charge Q, plus Q, minus Q, and plus sigma, minus sigma, and they had some area, etc. We know that would be the electric field. Now let's put an insulator in here. And see what's going to happen. Well, insulators, there's no free charge in the insulator, but the charge can deform. So deform is a strange thing to say a charge can do. Let me show you what I mean. If you have an atom that's just a positive nucleus and it's surrounded by a negative electron cloud, let's pretend it's beautifully symmetric, nice and round, and you apply this E naught to it, right, E naught gets there, then what's going to happen is if the nucleus sits here, the electrons are real light. They feel a force through the electric field. They want to go to the left. They can't completely come off because then well, they just can't do that, right? They're still attracted to each other, but this electric field is deforming them and putting the electrons more over here. So it creates a dipole moment. It creates a little internal electric field, E induced, we'll call it. Okay. Each little atom in this ideal world here makes a teeny little E induced. However, there's a bunch of atoms in the insulator, so they can make a response E induced. Okay. So when you put those together, then the field in the gap is just superposition. You just add them up. So it's E naught minus E induced. Okay. So what you see is that the electric field is reduced inside the capacitor. When you put in a material that has this ability, so we just have air. Air is very sparse. Air technically does this a little bit, but it's almost all vacuum. When you put in a solid material that can make a really big E induced, then it can really affect the field. We usually don't write it this way in terms of there's the original field minus something. It's usually you turn things around with a bunch of algebra we don't need to do, and we say E in the gap equals E naught over a big thing called K, the dielectric constant. Okay? So K of the insulator. So you can see the dielectric constant reduces the electric field, and how big it is depends on how good the material is at doing this. Different materials will make a larger induced field than other materials. In terms of the capacitor, though, what this tells us is we had a delta V naught, but then the delta V, the voltage, it takes to build up a certain charge difference, or thinking the other way, if you put on a certain charge, the amount of voltage that builds up is actually going to be delta V naught over the dielectric constant. Because because V equals ED, because the separation remains the same, so the electric field and the voltage are proportional to each other. So if the electric field drops by K, the delta V drops by K. So now we can start to think about how putting in the insulator affects the actual capacitor's behavior. We're going to look at a few dielectric constants. Air, it's approximately 1. We've done all of our calculations assuming the gap was empty, that it was vacuum. And that's how we got the electric field. Well, air has a very minuscule effect. There's such a low density of matter that it doesn't do much. So we just call it 1. So that's why we did our demo. We didn't evacuate the room. We went ahead and allowed there to be air. You can put plastic in the gap. and then K is about 3. So now that's really starting to reduce the electric field and could have a measurable effect on the capacitor. You could put essentially any insulator. We always do paper and plastic, so K, paper is about 3. Most of these sort of common insulators, it's somewhere 3 to 5, whatever. But then depending on the molecular structure of the insulator, you can get different values. For instance, water is very different. It's a liquid, and the water molecule has a large electric field in it. So all it has to do is let that molecule align the way it wants to in the gap field, and it'll reduce it significantly, and its K is about 80. So you get a big reduction if you put in water. So there's many things you can put in. So let's now look at our capacitor and see if we can see the effect of putting an insulator between the plates. So here we go. I'm going to charge it up by induction again. So bring in the rod and let the plates charge up, take the rod away. I think we got a reasonable number. Yeah, I got about 7. That's what I usually get. And now we're going to take this plastic sheet, just acrylic sheet, and drop it in the gap and see what it does. So it looks like it went down around, I think, about 3. Right? And then pull it back out, and it went back up. It may not have recovered all the way, but it definitely goes back up. So putting the plastic in changed the capacitor. It actually changed the voltage it needed to hold that charge. Let's look at what's happening sort of at a microscopic scale. So let's think, how could it be? If it lowered the voltage, it must have increased the capacitance, right? So let's see. So if we had the two plates here and here, if we think about it, when you drop in the insulator, and if it becomes what we call polarized, if the electrons sort of shift, you get a little bit of negative charge over here, and you get a little positive charge over here. So it's effectively making more capacitance, right? It's making more charged planes that are close to each other, and they're closer together than they were before. So you can see in this big picture view why we can increase the capacitance. So let's see how they do this with capacitors in the real world. So here's a real capacitor. It's got 4.7 millifarads of capacitance. That's quite a bit compared to our 18 picofarad little capacitor, and it's a lot smaller. So to find out, the only way to find out is to start to take it apart. So let me begin to cut on this little guy here. The package comes off pretty easy. Let me see. There we go. So this is just a label. We don't need the label, that's for sure. And then you can start to see what's going on inside. Yeah, so you can see it's just a metal can. One side is actually grounded to the can or connected to the can electrically. This side isn't. This is the side we want to go after here. And we'll just start gnawing it apart with this thing here. And the edge comes off. There's got to be something good in here to get 4.7 millifarads going. Let's see. You could be watching funny cats, or you could be watching this. Really, I think this is better. Okay, so now I've got the can sort of open. Oh, this is some sort of an electrode here. Let me see if I can pull the assembly out. Ooh, it's wet. It's wet. That's interesting. There's this little band is holding it together. So let's get that little band off of it, like that. And now, I don't know what chemicals are getting on my fingers, but there's something wet on here. And now, it may be alive. I'm not sure. Let's see. Let me get this piece to come off that piece. There we go. And now you can see it's starting to unwrap with wet paper. So we talked about water has a very high dielectric constant. So the acrylic using water is the gap, inside the gap, and you can see the paper is the gap. So the paper is between these two gray electrodes. So there's one on this side coming off, and now there's one on this side coming off. And you can see they have the paper in between. So they've put a dielectric in the gap, and they want a really big gap. So here's the gap. It's these two electrodes, and it comes apart more and more and more and more and more, and more. Look at that. Oh, it's still going. There it is, all the way to there. There's the whole capacitor. And there's an electrode on one side and an electrode on the other side. So that's how they get 4.7 millifarads in such a small package. Now I'm going to put it back together, and we'll put it back in the computer I took it out of. So there's one more thing I want to show you with capacitors. So almost all capacitors in the world are like this, the ones that go in circuits. This is the one that I just took apart, and I went ahead and wrapped it back up and put it all back together. But there are other uses for capacitors in the world. One is this. This is a stud sensor. So this is something that detects studs. So let's see if we calibrate it and then move it along. Yeah, it seems to be working pretty well. The way this works, though, is based on capacitance. So it's this little handheld device. It's not much to it. It's got a battery in it. The way it works is actually, if we look at it this way, it's got two little plates like this. And those are conducting plates, and those are a capacitor. Remember, a capacitor doesn't have to be two parallel plates. Any two conducting objects near each other that hold charge, technically, make a capacitor. So these things are sort of inside the instrument like this. And the instrument somehow measures the capacitance. It's applying charge, and you get an electric field that kind of goes like that. So the electric field lines will go into the space past the plates. Okay? So now if you put this against a wall, that's the kind of studs they're actually referring to. So if this is the wall of your house and you're looking for the stud being the big board in the wall that you can use to nail a heavy picture to, you want to know where it is, you hold it here, and when it first beeps, it's calibrating and figuring out what kind of a dielectric do I have here. If there's just air behind the wall, it measures a certain capacitance, because we know that putting a dielectric there will change the capacitance. So it measures the capacitance for nothing behind the wall, and then as it moves along, it'll beep when it sees a big change in the capacitance. And that occurs when the plates are here. Now you have a change in the dielectric in the field region, the region where the electric field is. And then when you move along and keep going, you're back to just an empty wall. So capacitance can be used in interesting ways other than just storing energy in a circuit.